All right. So, announcement number one. Hopefully you saw this on Piazza. Announcement number one is that there's no labs this week. No, you should be saying, oh no, what am I going to do? No labs because tomorrow's a day off. It's Veterans Day. And I couldn't figure out the best way to do that because I was originally thinking, oh good, when Thanksgiving comes along, we'll do the other labs. But then we get Tuesday. We're not going to do labs that week either. So we have 2 more labs left. One is going to be on hashing next week. And then 2 weeks after that will be our last lab on graphs, which we'll get to in a little bit. OK? So it's coming up. And hopefully homework 4, or rather homework 5 is coming along OK at this point. All right, remember it's due Friday night. And I'd really rather not have to give extensions on this because you have had 3 full weeks for an assignment that should not necessarily have taken you that long. And then homework 6, the last one, I'll actually put up probably Monday. I could probably put it up Sunday if you really wanted, but I'll give you a weekend off. Then you can start working on it Monday. And it'll be due probably Monday, the Monday of classes being done. And then if somebody needs another day or whatever, we'll talk about it. But there's like the reading period. But I don't want to go too far into that because we have to grade them. OK, any questions? Yeah?
The in-person grading.
The in-person grading, when we submit those, I'll tell you how that's going to work. You're basically going to sign up with TAs to meet them for about 20 minutes.
Okay. When?
At some point during the next week after that's due.
Like during the week of Thanksgiving.
Oh, you're right. It's going to be, is it Thanksgiving? Well, we'll figure it out. Don't worry. We'll have time to do that. Yeah. It'll probably initially be with either your lab TAs or me or something. We'll figure that out. OK? All right. Any other questions before we get going? Or yes?
The README file that's on Piazza, is that just if we're using Eclipse, or do we have to replace it no matter what?
The README file. You always have to replace the README file. The make file, you mean? What do you mean?
Wasn't there, like, when we're reading in the numbers for this thing, there's like a new...
Oh, it's not a new README file. There's a new, a different read list function, which you can use if you can use it if you're using Eclipse or not. It just makes it so you don't have to do the piping in of the numbers. That's all. It's easy to set up. It's easy to, but just don't. When you test your code, you'll need to take that out and replace it with the original. That's all, or at least put the original in there. Yeah, you don't have to replace it. No. And by the way, this one's a little different, where I am going to actually use your mains for the testing. OK, so all we're doing is basically piping in a bunch of numbers, timing how long it takes for them to run, and seeing if they're in the correct order. Right? And that's really about all there is. And then we'll have lots of statistics for when we come to the in-person grading. You can actually say, hey, you can describe what sorts you did. You can describe the asymptotic complexity for them. You can describe any challenges you had. And you can also describe why the times came out the way they did. Right? So those are the big things you'll be talking about in the in-person grading. Yeah, right.
Question on commenting.
Yeah.
Since part of this, like, we're just basically taking your selection sort files, putting them into new ones, and then changing anything that needs to be changed.
Yeah.
Do we comment what you wrote, even though it's technically like our new file?
No, you don't have to. I mean, you should probably have. You should have comments on the stuff that's pertinent to the actual sort. Right? That's the way the commenting should be. Don't stress about like changing other new comments and things. Anything else? OK. All right. So today I think this is an interesting class today because we're talking about some more about hashing and hash tables. OK. Does somebody want to remind me what a hash table actually involves? We haven't really gotten into hash tables per se. But what does hashing involve? What does hashing involve? Somebody from like that side who hasn't answered. Well, we've got some answers over here today of this side. Somebody, what is hashing all about? Should we redo last week's lesson on hashing? Let's say I have a key and it's a number, right? What can I do to that key to get it into a hash table? Yeah, Susanna. There you go. It's a mathematical function that you apply to the key, and that determines where in some table, generally an array, it goes, right? And then sometimes we can have 2 keys hashing to the same value, and we figured out there's one way in particular to deal with that. Which what did we call that? Do you remember? Chaining. Yeah, we used like a linked list to actually do it. I'll show you that again. So yeah, so keep those in mind. That's the basics of hashing. We're going to go into more details about the actual hashing itself and how to avoid some of those collisions when you have chaining, or when you maybe use chaining before. And then we're going to go into some other issues about hashes in general. And then we're going to talk a little bit about what we call cryptographic hashing, which is actually kind of a fun topic. Actually, as a naval officer, one of my I was originally called a cryptologist. And we talked about some of these things like cryptographic hashing and all that. So it's kind of fun stuff. Okay? In fact, I'm really tired today because I got back at 6 a.m. off a flight from Seattle last night. So again, if I fall over, you know, I'm probably not dead, but you might want to call 911 anyway. OK, also got a quick little UNIX tip of the day. This could come in handy if you wanted to for this assignment, but it's another way to talk about the small little programs that UNIX has, right, and linking them together so that your text or data or whatever goes through a bunch of these programs. OK, it's actually called a pipe, and it's a vertical bar. And let's see, on my keyboard is above the backslash. Some other keyboards it's in various places. But that's what we're going to talk about for that. And then we'll go into more on hashing. OK? All right, so what is this piping thing? Well, you know how we use the little alligator or the little less thans or greater thans to send data into our program for this assignment, right? Well, you can also have a program go to another program, the output of one program go to the input of the other program, and you don't you don't do it with the little less than or greater than. You actually do it with this vertical pipe command. Okay? And think of it like a pipe, like you're sending data down this pipe, and at each stage there's another program that's going to do something to it. Okay? As I mentioned the other day, one of the big killer functions of UNIX was this ability to have these tiny little programs that you can write, and then lots of those tiny little programs that each do their own little thing. Okay? Hopefully they do it pretty well, and then you do one thing after the other after the other. Okay? So it turns out that what happens is you actually, when you're piping things through, like all the programs could be running at the exact same time. Like program 1 is doing the program 1 takes some data, sends it to program 2. While program 2 is working on data, program 1 is working on the next set of data, and 3 and 4 and 5. So it actually speeds things up as well. Okay? Here's how we actually do it. We can say, for instance, ls-a1. Let me show you that. If we do ls-a1, it will give a list of all the files just in my folder, right? And I've got a ton of them here because this is my regular Mac folder, right? It's got a whole bunch of files. The first two happen to be dot and dot dot. Anyone know what those ones stand for? Alex, what do those stand for?
This directory and parent directory?
Yeah, dot stands for this directory, and the dot dot stands for the parent directory. It's just a shortcut. But let's say I wanted to count all the files in my directory without those two. I could just subtract 2. But what I could do is this. Or what if I wanted to list all the ones without, whoops, what if I wanted to list all the ones without those two? And I know they come at the top. There's a program called tail, which says, give me the last part of whatever the output is. And you can say, in this case, -n+3, which says, don't do the first line or the second line. Start at the third line. OK, so if we do ls-a1 pipe tail-n, what did I say, +3? +3, right? It will list all the files again, and it does not list the first two, like that. Okay, so that's one way to pipe. So we've piped the output of ls into tail, and then we've said just don't give me the first 2 lines, as it turns out. Okay, so that's one thing we could do. Let's say we wanted to count all these files. Well, there's a program called word count. So if we pipe the output of, it's tough to see, hold on. If we pipe the output of our command here through this command called word count, it's going to go first do the directory. While it's doing the directory, it's going to be sending the output to tail, which is then going to be sending the output to word count. And if you do that, it says there are 221 files in my directory. Right? So we pipe stuff through the directory, or through the files. You can do that for lots of different things. If you want to use sed or grep or other functions, you can pipe. And I've done it for probably 7 or 8 different things before, trying to get my data exactly the way I want it. Okay? For instance, let's say I wanted to list all my files, except for the first 2, and then not anything that says the word temp in it. So for instance, this one would be gone, right? You could do grep, which is that one that says find various pieces. Dash V happens to say, if you find that, ignore it. Like, don't give me that output. And then what that'll do, oops, maybe it won't. Hang on. Tail dash, let's see, dash V. I'm going to make a liar out of myself here. Grep. Oh, I got to put something to grep for. Temp. There we go. All right. And there we go. And now notice TEMP is missing because it took it out. Okay? So you can keep piping through. If you wanted to do also, you could pipe through grep-v for TMP as well. And then anything that has TMP in it will be gone too. So you can see how you can do boop, boop, boop all through all these different files. Yeah?
Slightly unrelated Linux question. When you, not in tail, but in the other ones, when it came up, the different colors and the different
Yeah.
files that they were, it's say you have a file that you know it's executable, but you don't know how to run it. Is there a way to, say, what's the command I would need to run this, or not really?
Not really. No, there's no real way to say what's the command I need to do it. But if you want to try running it, you can change the permissions to be executable, and then you can just do / whatever the name is, and it will try to run it. And if it works, it works, and if it doesn't, it'll crash. That's that. All right. Any other comments or questions on piping? You will see that a lot when you do other Unixy type things. OK. All right. I forgot to show you this the other day. This is our hash table written in a different programming language. It happens to be written in lolcat programming language, which somebody actually wrote a program that will, or a compiler to take this and turn it into code, right? It'll actually compile. I has a word dictionary, right? K thanks bye is the exit or whatever, right? So, yeah. It's called lolcat, I think. Lolcode, is that what it is? Lolcode? Yeah. So, anyway. Maybe we should teach Comp 11 in this and then Comp 15 in this too. Yeah. I don't.
Can I put that on my resume?
Can you put it on your resume? Sure. Yeah. There are thousands of different. If you've never seen how many different programming languages there are, right? List of programming languages, right? List of programming languages is hopefully going to come up here. Maybe it won't. There it goes. List of programming languages. And see all those lists? There's hundreds and hundreds and hundreds of different programming languages, right?
Is there a standard you have to meet to be considered a valid programming language?
That's a very good question. Is there a standard you have to meet to become a valid programming language? Not really. However, you could go down the route of what we call being, quote, Turing complete, which means that if you can write it in one language, then you can write it in any language, basically. That's kind of a very broad definition of Turing complete. It means if you can compute it using a programming language, you can compute it using any other language that meets that same definition of completeness. You will learn all about that when you take Comp 170, Theory of Computation. Yeah. All right. So back to hashing. So in C++, for what it's worth. This is a compressed version of what I showed you the other day, which is just, in the last lesson, we saw that one way that we had to deal with collisions was this chaining, okay, that we already talked about. Basically having some sort of linked list or other structure in each bucket that says, OK, look, there's other things than there's more than one thing here. There's either none or more than one, and it's a linked list of stuff, OK? Well, the problem with that, right, the problem with chaining, OK, is, well, it's not a big deal, except that you have to have some other data structure in your data structure, right? Basically, whenever you collide, you have to add to this one area of the table, okay? And you have to add this additional structure, which makes it a little more it makes it harder to use as far as a single hash table. We would like our single hash table to be one array, and that's it. But in this case, we have to add another data structure. It's a linked list. We have to make that code, or an array, or something else. We have to worry about expanding it, or pointers, and all that. And sometimes we just rather not worry about that, and it's not necessarily that fast. Okay? So there are some other interesting ideas here. Okay? Let's say that we had the following hash table up here, right? It's got 1, 2, 3, 4, 5, 6, 7 buckets in it. The first two happen to be filled with some data, right? And then the next two are empty, and the third one's filled, and the next one's empty, and the last one's filled there, and it just kind of keeps going along. Okay? If we hash to the first location with some new value, right? Before, we would have to create a linked list and blah, blah, blah. Okay? What if we can figure out that the next available space is this one and just put it there? Right? That's a different way to do it. Aaron?
And how would we be able to access it from our hash?
How would we be able to access it? Well, there's lots of different ways to do that. But that's kind of the idea here. Okay? Let's see, I think the next one here has, yeah. If we hash to this location, okay, and it's filled, and we know it's filled because it's not null or it's not whatever, sometimes we call, like if it's just an integer, we might put an integer there that means, hey, this is empty. Like remember in last assignment, I had you to use maxint and minint for the like the minimum in a no node tree, right? Well, it's the same sort of idea. You can put a value here that you know you'll never be able to never use, and that could be what we call our sentinel, which says, hey, this is not filled. But anyway, so you think it's this in this one, right? Or you hash it to the first one, and that one's filled. Well, the easiest thing to do is go to the one next door and say, hey, are you filled? Right? You just add 1 to the actual hash code. You hash it to some value. And remember, a hash code is just a number that designates a bucket in an array. You hash it to that one. You go to the next one. You say, are you filled? Right? And that one's filled. So then it goes to the next one. And when it gets to the next one, it says, oh, I'm empty. I'm going to put the value there. Now, Aaron, back to your question. How would we find out where like this one is? What kind of ideas might we have to do that? What do you think, Charlie?
I was going to say take the inverse of the hash function.
The inverse of the hash function. I'm not sure what that means.
Well, so I mean that when you apply the hash key to the function, then it gives you the indice, right? So if you take the indice and apply the inverse of the function, you get an empty hash.
Most of the time, we can't do that. You can't do most hash functions are what we call one way, which means you can't go backwards for them. Right? There's various reasons. Like if you're doing a modulus, like remember, any number of things can go in this bucket. We already that's kind of the whole point of this issue we've got, right? So that's we can there's other different ways of doing it. Loretta, what do you think?
I feel like it's gonna be really messy. Could you put a pointer from where it's supposed to go to where it currently is?
It's easier than that. Can you put a pointer there? It's actually easier than that. What do you think, Tim?
If you follow the same logic you had used to place it, you'd reach it.
Yeah. So what else would you have to store there besides the data? You'd have to also store the key there, right? So let's say we store the key here, and we go and let's say the key here is 2 and then 3 and then 4, right? And we're looking for 4. Well, if we look for 4 and this one's 2, it's filled and it's not 4. So therefore we go to the next one. It's 3, so it's filled, but it's not 4. We go to the next one. It's 4. We've found it. That's how you can do it. So you have to store your key as well. Alex?
But then what if, like, say
It's on the next page.
we drop something in key 2, or we drop something where key 3 is.
Sure.
Right? And then something comes along that actually has key 3.
Sure. Where does it go? If something's in key 3, where does it go? It goes to the next one, right? And so collisions, there's like kind of a collision begets collision in some sort, right? Some sense, right? So yeah, you can do that, but it doesn't really matter because you're still going to check what is in key 3, and if it's not what you're looking for, or if you're putting something there and if you're putting something in that one and it's filled already, you just go to the next one and see if it's filled.
But in a crowded hash table, wouldn't that result in like a really long linear?
Yeah, it might. Yeah, linear searches are not that great because of that exact problem. You can sometimes end up having hashes. You can have to go a long distance in there. Let's see. Somebody else had a question back there. Anybody beside? I know it wasn't up front. No. Okay. Aaron and then Jordan and then Rada and then yeah.
Oh, well, what if we had a specifier in our program that said if you're trying to put something somewhere and it belongs there and the thing that's already there doesn't, like if you said like
Oh, I see.
put in key 3, we can bump over it, and then the thing that actually belongs we can put there, and
Yeah.
then we would just have less stuff to walk to.
You're getting kind of complicated. You'd still have just as much stuff to walk to. I mean,
Yeah, because when you're walking for the other one, you'd walk one more space.
yeah, you'd walk one more space anyway. I mean, I think you're just making it. This is supposed to be a pretty low. Like, remember, it's supposed to be fast, and it happens quickly because we just run through these things in a particular. Like, we don't make lots of extra corner cases and things. Okay, let's step back because I think I saw some faces are like, I don't really get what's going on here. We hash a value and it's key 3. We want to put key 3, yeah, well, let's go back one. we want to put key 3, all right? And key 3 hashes to here. And we check, and it's actually key 1 because it's filled. We can't put it there. So we check the next one. We add 1 to the value, and we check the next one. And by the way, we do it mod the table size, so it wraps around. Okay? Check the next one. It's filled. So we got to go to the next one. We go to the next one. We put it there because it's not filled. We're done. Checking for the key, one second, Annie. Checking for the key is the other way around. You say, if we're looking for key 3, we look in the first bucket where it should be. That's where it hashes to originally. Key 1 is there, so it's not ours. Because key 1 is there, we go to the next one, and we look at key 2. Key 2, it's not ours, but it is something, so we go to the next one, and there's the one we're looking for. Let's say we looked for key 4, and it also hashed here. We would look here, 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 here. It's empty, so what do we return? What do we say? It's not in the table. Okay, you get that? Like, that's the other difference about that. Jordan, you had another question, then we'll go on. Yeah.
I understand why this is better than just an array of an array.
Why is it better than it? Well, what do you think?
Or chaining.
Yeah, why is it not better? Why is it better? It's less data structure. Like there's no extra data structure about this. There's this one array now, right? That's pretty much the reason. Now, linear chaining is not like linear probing, which is what this is called, is not the best way to do it. Okay, but yeah, we'll go through some others. But this is there are some downsides to this too. But one of the upsides happens to be it's less data structures you have to worry about. There's one data structure.
I'm confused
Jenny?
about why it won't get out of order.
It will get out of order, but who cares? It doesn't matter if it's out of order. There's no order to a hash table. Like, it doesn't really matter, right? The point is we have to just find the value whether it's there or not, and the data associated with it. That's really the big thing. Yeah. Go ahead.
I had thought that with hash tables, its position in the array had to do with what it was.
It does. The hash table, the position in the array has to do with the hash itself. But if you're using this strategy, right, then it's not going to be there, but you have to check there first. And then it's going to not be there, but you have to check there. Then it's going to be here. So it does slow you down a little bit, but it's because we have to do something about collisions, because remember, collisions will happen. Can't get away from collisions. Okay? Loretta?
You know,
Okay.
if we, so like say we put it into key 3, we already put it into third position.
Yeah.
We go back to search for it, but in between there we take it out completely.
Ah, we'll get there. What happens when you delete ones? We will get there. You're one step ahead. Yeah.
Seems like it's really slow looking for things that aren't there. Just because it's going to search the next, the next slot and the next slot and the next slot.
It depends how filled your array is, right? It depends what your load factor is. That's a very good point.
But if you pulled something out, it doesn't know whether that was there to be.
Well, we'll get to that. We'll get to that in a minute. We'll get to what happens in that case in a sec. Yeah, good question. Somebody else over here had a question? Yeah, so Sana.
What if you don't have empty slots to put it in?
Yeah, well, there's one of the downsides to this, right? If we filled every slot and then kept going around, this would loop forever, right? And we'd be in trouble. So you have to be very careful with your load factor. You have to continually calculate your load factor. And if it gets to a threshold below or above what you want it to be, you have to figure out how to redo this hash table in a bigger array, which is another thing altogether. We'll get there too. Yeah, Ben.
Ideally, aren't you coming up with a hash that makes it so that you should really only be doing this like a handful of times?
Yes, your hash should be relatively random. Yeah, hopefully your hash puts the values not all here. That would be silly, right? It would put one here and then here and then here and then here. So yes, is that your point?
Or you come up with a, so in the same way that we were all around the room, like a bad hash was one
Right.
where we were all crowded around one space. But if we came up with hash that spread us out,
Yeah.
there were less.
Exactly. There are fewer times that you're going to need to worry about that. Yeah, so that's hopefully what you're doing. We're not hashing everything to a very small number of buckets. That's a good point. That will limit the number of times we have to do this. That would also limit the number of chaining we'd have to do too, for what it's worth. But that would limit it. But there are going to be collisions of some sort. So you have to deal with collisions in some way or another. Yeah. Question or comment?
Is it possible to implement dynamic hashing? Like,
What do you mean?
that your hashing function can change so long as the following iterations are consistent and watch the previous iterations?
Yeah.
Expand it and then change your function.
Yeah, you can change your function. There's another way of doing this kind of hashing I'll show you in a sec, which is kind of related to that. But yeah, you could. I mean, look, you can come up with any way that you want. As long as it is consistent, it would still technically be a hash table. Sure. OK, any other questions on this stuff? OK. Here's another way to do it. So one of the issues we already found was like you're jumping. If you had a whole bunch of things next to each other, you're going to have to look through them all. Bing, 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 until you get to the end. There's a slightly better way of doing this. We call this quadratic hashing. Okay, it's a quadratic polynomial. I guess it's searching, which is what you do is you just, instead of adding 1 to it, you add, or instead of like first you add 0, then you add 1, then you add 2. Then you add 0, 1. 4, 9, 16. You square the amount you're adding to it each time, okay? And then so what you do is you jump over a bunch if there's a bunch in a row. So it helps a little bit if there's lots of things that get bunched up into one particular portion of the hash table, okay? You have to be a little careful with these strange methods like this because sometimes you can jump so that you might miss particular empty spots, and then you have to worry. Then you get into that same problem where you go through your whole table. There might be empty spots, but you've never hit any of them because you're repeating back at the one you started with. So you just got to be a little careful with that. But it's a better way to do it if there's lots of hashes in a row, because it'll jump over a lot of them. Okay, so here's the example. If we go, not a great example actually. If we go here and then we go here, the next one is going to be plus 2 squared, so it'll be over here. And it will put it way over there. So it jumps over some. In this case, it jumped over empty ones, but it'll jump over various parts of the hash table. Yeah?
Wait, if our algorithm stops looking and just says it's not there, as soon as we hit like
An empty space.
an empty
Yeah.
space, what happens if an empty space shows up for some other reason? Like
If we removed one, we'll get there. You guys are thinking ahead. That's part of it. There's no other reason for a removed one to be there. Or there's no other reason for it to be empty except for removing one, which we'll get to. Okay? Okay, so this is another way to do the quadratic one. Okay? All these strategies are called open addressing strategies. Basically, you're changing the address in the hash. Another one is to use a second hash function on top of your first hash function. Right? So what you do is you use the first hash function, it goes here, and then you have some other hash function that you can multiply by whatever attempt you're doing to go use the next hash function, and that actually randomizes a bit more. So you can get kind of your whole idea is to kind of randomize where you're putting things in a tree. That actually helps a little bit too. Okay, that's called double hashing. The lab will go over this next week. Okay, double hashing. Yeah, Jordan?
So the input to the second hash function is the number of times the first.
No, it's actually the same. It's the same. Yeah, you can do a lot of different ways, but it's generally the same input. For the lab, it will be very specific about what your double hash is in this case. Okay. Yeah, Ben.
So when two identical elements are put in, do they take up the exact same space?
Depends how you do it. Generally not. I mean, it depends. As I said, the Python language has its hash table where if you put something that's identical with the identical key, it replaces what was there. So other ways you can do it, you can have them both in there, but you only return one, or you can return all of them, or there's various methods for figuring that out. Yep.
Does the order matter? Like, I suppose it matters with the implementation, but when we add more elements into the chain, does it matter how we keep them?
No, it doesn't matter. It doesn't matter how you keep them. In fact, remember, there's no way to find a max or a min in a hash table. It's just not possible because of the way hash tables are built. So you can't really figure out an ordering in that sense.
Wait.
No. You can't figure out an ordering. Now, you could go through, if you knew all the keys, you go through all the keys and then do some sort function on all those keys and then do it. But
Look for one?
no, you can't. Well, no, you can't just look for one because you mean you would have to hash one and look for it? That would be the key. You can't really do that. I mean, I suppose you could, but you wouldn't know the min if it doesn't exist. It's a harder problem than that, yeah. OK, so that's one. Yeah, so this is the double hashing one. Let's see. So we talked about this. If the table's full, the algorithm might not even terminate. So you have to be really careful. OK, you have to keep an eye on your load factor here. OK, remember what our load factor was. Our load factor is the number of keys that you've actually got stored divided by the number of buckets you have available to store them in, how big your array is, right? Generally, most hash table implementations keep it between 0.7, 0.8, somewhere around there. Like I said, for your final project, if you do a hash table, I would drop that even lower, depending on the hashing scheme you're using. Because we're going to have a big data set for this next project, but you still probably have enough data to make it a little lower. So what you want is, if it's above 1, you're in well, if it was 1, you'd be done. Because you couldn't find a place. Everything would be filled. You'd never find a place. So that would break. So you can't make it 1, but you should make it enough less than 1 so you're not taking forever to search. Okay? Searching does take time in these methods. Okay? All right. Now, here's the question. And so I'm going to let you guys think about this for a minute. If we do have to change our dynamic array, so it's this big, and then it's like 10 elements long, and then we want to make it 20 elements long because we've got a load factor. We want to decrease our load factor. How do we expand a hash table? Think about that. Talk with your neighbor for a couple minutes about how you expand a hash table. Okay? It's a little tricky. Okay, let's see what we can do here. I figured, why don't we just do a little example? Just a little hashing example here, and we'll see what we'll do that. Then I'm going to let you guys see if you can answer what happens. Okay, here's what I've got. All right, we've got a hash table that we have 4 spots available for it, and I'm going to try to hash 10A, 10 being the key, A being the value that's associated with that key, 20 for B, 30 for C, 40 for D. Okay. And we're going to put this in. Forget about I don't care what the hash function is right now, but I'm saying that it maps to 0 for 10, 5 for 20, 30 for 1, and 40 for 2. Okay? All right. Where are we going to put 10? Position 0, because it maps to 0. And we're going to put both 10 and A in there, right? Because you have to store the key and the value. OK. How about 20? Where's that going to go? You should probably do modulus the table size, which in this case is 4, right? Modulus 4 for the 1, modulus 4 for the 2, right? And that's going to tell you where to put it in the table. So what's 5 modulus 4? 1. So that's going to mean 20 and B is going to go in position 1. OK. Hash of 30 we said maps to 1. 1 modulus 4 gives you 1, look, 20 is already there. Let's use linear probing. Where are we going to check next? Position 2, is anybody there? No, so we're going to put 30 there and C there. I promise I didn't make it come out in order like this. And then finally, we've got 40, which maps to 2. Our hash table goes to 2. 2 modulus 4 is what? 2, right? So it's going to try to go in here, but it's not, so it's going to check here, and it's going to be there. So this is what our hash table is going to look like now. OK, let's just do a search and see if we can find one. Let's search for 20. Where do we start looking? At 1. Oh, it's there. Good. Let's look for 30. Where do we start looking? At 1. It's not there, but is it filled? Yeah, so then we know we go on to the next one. Is this 30? It is. So that's how we do the searching. OK, so everybody's good on inserting. OK, now our hash table has a load factor of 1. This is not good, right? So what are we going to have to do? We're going to have to expand. What were your ideas for expanding? What did you guys think? Ben, what do you think?
You add elements in between your already existing elements. Or
OK, so what's going to go over here then in this new 8-member array?
You just multiply.
So you're going to put 10a, and then here 20b, and then 30c, and then 40d. OK, great. Let's search for 30. Where are we going to look? At position 1. Nope, 30 is not in our table.
Yeah, would you then factor that into your?
Oh, so you're trying to change our hash function. We're not allowed to change our hash function.
So you couldn't do like the
No. Can't change your hash function in this case. Yeah, good question. Good idea, though. But in our case, we're not going to let. Now, that might be another way to do it, actually. Every time you expand, you like double your hash function somehow. That's not a bad idea. But then when you wrap around, we might have trouble, too. Right? Because let's look for, yeah, what if we did 4? It's, I mean, then how would we find 4? Right? Or 40, rather. It should go to, now you're going to do times 2. Is that what you're going to do? OK, so what's going to be? It's going to be 4. We're going to look in position 4. 0, 1, 2, 3, 4. I guess it works in this case. If you're wrapping around, I don't think that's going to work very well.
Well, it doesn't work because
Then you walk to 5.
Oh, that was 30. What were we looking for? We were looking for 30.
40.
Oh, we were looking for 40.
Yeah.
Yeah, we were looking for 40. Not there, right? And then we'd look the next one, not there. So good idea. Not going to work in this case. Yeah?
What if you just mod it to the new table size?
What do you mean mod it to the new table size?
I mean, you expanded your new.
OK, so go ahead and let's try it. Let's try it. So what's going to go here? 10 and A. OK, and then what?
Then you would do 5 mod 8 for 20.
Oh, I see. So you're going to rehash everybody. Ah, OK. So then you're going to do 5 mod 8. Instead of 4, it's just going to be, so you're going to go through every element in your original table and rehash it. OK, that actually I think would probably work, right? Because now it's going to be, for 20, it's going to be 5 mod 8, which is 5, right? So that's going to be 20b. And then 30 is going to be 1 mod 8, which is 1 again, so 30c. OK, and then 40 is going to be 2 mod 8, which is 2, so 40d. Can you find them all? Sure you can, yeah. So this actually works. So yeah, that would be perfect. Now, what other ideas did you guys have? This one actually is a very good idea. What other ideas do you have? A question about this one? OK.
But what if you already you had like, that's fine with 4 things, but if you had like a million things already in your table?
Yeah, it's slow.
Okay.
Yeah, I mean, the problem is, so either way, it's going to be relatively slow. Because remember, when we're expanding a dynamic array, don't we already have to at least copy everybody over? And we already said that our hash function should be relatively fast, right? So all we're doing is we're rehashing each one and then putting it in the new table. So that's what we're actually doing. Yeah, question.
Also, what if your hash is made to turn out numbers that were meant to fit in your old array? So it's always going to turn out something 1 through 4.
That would be a bad hash
Well, but then
function.
But if you say it was like 1 through 1,000, and you didn't think you were going to get like more.
I know, but you can't make those. I mean, if you're gonna think that, then you've got a different problem on your hands.
So we should write hash functions that use all the integers.
Use hash function.
Or that we should write hash functions that will yield all the integers, like all.
It's not a bad idea. You mean so you can mod it to the table?
You can expand them as far as you can expand your.
No, you can always expand it. You can always expand this as much as you want. Remember, you're just modding on the table size. The only thing we're changing is modding on the table size.
Right, but my point is you want, it doesn't have, so you want a hash that's not just evenly distributed for a table of the size you think you're going to have, but of any
Yeah,
size.
sure. But remember, the modulus part is really what you're going to get that movement all through the table.
Of course, yeah.
And if you do, yeah, and there's other good hash functions that use different modulus ones. Question, Logan, and then. Sorry.
On that. So, I mean, but hash functions have to have a limited number of buckets, right? So
Yeah, hash functions have to have a limited
so
space.
then you can't really expand. You can't expand your very far beyond that, otherwise you just get a massive linear probing situation. Because if you have a list, an array that's substantially larger than the number of buckets, then you just end up probing through a lot of things because it's trying to collide a lot, right?
I'm not sure I get what you're talking about. If you expand this, the load factor just went from 1 to 0.5. So you're going to get many fewer collisions. Notice we didn't have any collisions in that last one. Or I guess we had one, but that was it.
But I mean, if you had, you had say 100 buckets,
Yeah,
right?
yeah.
And then you suddenly had an array that was length 400, then you'd automatically be, and you wanted to put 400 elements in, or 300 elements, and you get a lot of collisions.
You get a lot of collisions. So you'd want to double when the load factor gets above, say, 0.7, 0.8, rehash. That's the other thing. Sorry, you had a question? We had another couple questions over here. No. Okay, go ahead, and then Ben.
You want to make your hash function scalable, so like regardless of the size of your table, it should work, right?
Yes. Your hash function, but your hash function, remember the hash function should come up with a number much bigger than the number of buckets you have. That's probably the general idea. Your hash function is best if it comes up with isn't that what you were kind of saying? Your hash function, the best hash function is one that's going to come up with a really big number that you take the modulus of and put it somewhere in your limited bucket size.
So it's not that your hash function is taking into account the size of your table.
Right.
When you mod it.
Yeah, the modding is what does that. Yeah. Okay, good. What other? Did you get a question earlier? What was it?
Yeah, no, I'm good.
Okay. All right, Jordan.
Good.
Okay. Anybody else? Okay. So this is actually if you had other ideas, they may very well work. What you can't do is just copy these straight over. You have to do some sort of rehashing process to do it. Otherwise, you'll lose the hash, and then you'll like lose the ability to find that hash because there is no ordering. And if you start spreading things out, you're going to be in trouble. Okay. So that's all what we just talked about, right? Rehash the keys, reinsert them into the table. Does take time, but hopefully your hash function is kind of fast, right? There is this thing called consistent hashing, and maybe that's what you guys were getting at. There is this thing called consistent hashing, which most of the keys don't change their position, right? You don't have to actually move them, or you don't have to actually rehash them if they have certain properties. It's hard to have consistent hashing, though. Okay, hard to get that. And I don't know there's various papers you can read about that. Okay. All right, so here's the question a bunch of you guys asked earlier. What happens if we try to remove an element from this open addressing scheme? If let's say that all three of these, key 1, 2, and 3, happen to hash to key position, the first one here. If we remove 1, right, then we're in trouble, right? We now have an issue where this one's empty. If we try to go find key 3, we look here, it says, oh, I'm empty. You're done, right? Because you'll never look on the next 2 because you'll think that you're done already because it's empty, because you would have put 1 there. What solutions might we have for this? What do you think?
It seems kind of
Maggie?
inefficient,
Uh-huh.
but you can go to the next empty one and then like work your way back and find if any of them are supposed to have.
Oh, that's interesting. Yeah, you could do that, right? You could say, fine, this one's the one I deleted. Let's go. This one could be part of it. This one could be part of it. This one's definitely not. So we know that these ones are the only ones that could be there. And then we like move some over there. Yeah. In fact, how many would you have to move?
1.
Just 1, right? You'd have to just move 1. So that's not a bad idea. It's not a bad idea at all, actually. Okay. So that is one potential way to do it. I don't think I actually talked about that. That's definitely a potential way to do it. Jean-Marie?
You could have a marker that says empty but useful.
Yeah, you could do that. Yeah, you could have a marker that says deleted. In fact, that's the first solution I came up with, right? Was you could say it's deleted, but then if you want to put something there, you're allowed to. right? So you go there and say, oh, it's deleted. We still have to check the next one. And then you just go put one there. The next time you insert, it goes there, right? So that would work. Ben?
But doesn't that make it so that if you have an array of 10 elements that you fill up completely and then you delete 9 of them and you're trying to search for one, you have to go through the whole array?
Yeah, you would.
So
You would.
at worst case, like to actually find an element, that would be better than 10, right?
Yeah, sure. It would, right. And remember, we're trying to have our load factor be low enough so that doesn't happen. Yeah, you can degrade these things pretty well, but you don't want to. You want to have your load factor be low enough so it's still got constant behavior. Okay?
If you inserted an element after you deleted something, wouldn't there be a situation where it would think that that thing has been filled, and so it's trying to search past it, even though at the time that you inserted it, it was empty?
I'm not sure I get what you mean. Let's say in this case we get what happens when it's deleted, right?
Yeah.
It looks here, it says, oh, it's been deleted. We have to keep searching, right? So if we're searching for something, if we're inserting, we just put it right there, because it's a deleted one, and we know it's a free one for us to use, right? So yeah. Now, I guess what's your question now? If we put another, let's say we have key 4 that goes in there, we can still find key 3, because now we look here, it says key 4. Okay, that's filled. We look at the next one, key 2, and then key 3, and we find it, right? If we're looking for key 4, it's right there. So I don't get the issue.
I don't know if I do either.
Okay. All right, fair enough. If you come up with it again, let me know. Yeah, Charlie.
I was going to suggest instead of taking one of the keys that it would be appropriate
Uh-huh.
to switch into, I would suggest finding the lost one.
Well, that's what Maggie was saying. Yeah, find the last one and put the last one there, right? You'd have to look through all of them until you get to an empty spot, and then you'd say do that. Now, yes, if you've got a whole long chain, that does take some time, and it might be just as well to just leave a deleted spot there and do that. But you could certainly do that. The next time you insert one, right? The next time an element's fine, it could go into the deleted spot. Or the next time you find anyone, like let's say we go and look for key 2. Well, we know that it should have been back there. So at least we were doing something to get to key 2 that we wanted. And at that point, take the time and then move it back there and make this one deleted. So you could eventually get everybody back to where they need to go. So, Sandra?
Can you sort where the last key of a certain position is on the first one? It's like where, like say that, or like where was deleted? Say, oh yeah, the last.
Oh, I see. For a faster insert.
Yes.
For a faster insert.
You just look at that place and switch it instead of having to go through every.
Let's see. I'm not sure that would necessarily. Well, the problem is lots of things could go in there that don't hash to that anyway, right? So, I mean. Like someone from back here could go bing, 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 and then end up in that one. But I see what you mean, though. I see what you mean for every position. Say, hey, if you hash to this position, where's the last one in that? That's not a bad idea. I don't know. That might be more efficient. Yeah, it might not be a bad idea. Yeah, to keep a little last one so you know where to go to the last one to insert. Not a bad idea. Yeah, I think that won't help you for searching, but it'll help you for inserting. Yeah.
But if we mark the spot as deleted, and then we drop something else like unrelated to it, would that mess up our search later?
Why? You're still going to search here, and something's going to be there, and then you're going to go to the next one until you find it.
What if the original, like the first something?
It
Like, you know how
doesn't matter. There is no first something. Like it doesn't matter what I mean, I see what you mean, but it doesn't matter at this point. If it's filled, and you got to move on. And it doesn't matter what's there. You're not trying to say, oh, does this one really belong here? You don't care.
Wait, one more question.
Yeah.
Is the heap circular?
Is the heap, you mean is the array circular?
Yeah, is the array circular?
In a sense it is, because if you hash something and it's like 27, you do 27 mod 8, and it goes back to whatever 27 mod 8 is. So yes, it's circular in that sense. Yeah. If you get to the end of the array and it's filled, you wrap around to the beginning and you say filled, filled, filled. Okay, it goes there. Okay, so that's how those ones work. Okay. All right. Any other questions on that? Found it there. Okay. Let's see. The next time it's fine, go into the deleted spot, move to the next spot. All right. So that's the big thing on hashing. Those are all the things that you're going to need to know how to do. Now let's talk about some more like things that you have to know about but not necessarily know how to do. Okay? Is there a perfect hash function? Like in other words, can you take a set of values and know that we're always going to be able to hash them without any collisions? For generic data that you don't know ahead of time, no. you can't say, I'm going to come up with a hash function that will always randomly place them without a collision. We already kind of realized there's a birthday problem issue and that. But if you know the set of keys ahead of time, you can figure it out. We did that already with the two-letter words. That was actually a perfect hash because we knew that the two-letter words would never collide with another two-letter word. Right? So for very small, like simple types of hash functions and data, we can do it. Right? It's not necessarily the easiest, or it's not the best way to do it because you've got to have those keys ahead of time. But if you already know the keys ahead of time, then you can figure out a hash function that was perfect.
That function one-to-one, so
Say again?
what if you made the function one-to-one?
Yeah, if you made the function one-to-one, sure. Yep. If you made it one-to-one, if you had 1,000 keys and you had 1,000 elements, you could figure out how to do that. Sure. You just have to know the keys ahead of time to know that there's a one-to-one relationship or know how to put the one-to-one relationship. Yeah, good. OK. There are various papers you can read about this and about how to do this. So if you want more information about it, go ahead and read the papers about that. They're kind of interesting, a little intense. Yeah.
Is there any one location that kind of looks at all this research and says oh, here's what people have come up with, or is it really scattered?
There probably are various sources that say, if you look up hash tables on Wikipedia, they talk about, hey, how do they figure out that the load factor is the right load factor, and what's the best addressing schemes that people have used, and so forth. The other way to do it is to say, the people who create the Java programming language or C++ standard libraries, they're going to pick the best ones for these. So if you go and look at those code, you'll probably know. And lots of people look at these things. That's how you kind of know. Yeah. OK. We have a perfect hash function. It could be a one-to-one, and we have exactly the same number of keys as the number of elements. Or it could be longer, and just everything happens to not collide. If you have a hash function that fits exactly into your hash table, and all the elements are filled, it's called a perfect hash function. It's called a minimal perfect hash function. And it's also hard to achieve, but it's possible. And there's some other papers. There's another paper here I can point you to if you want to go get more details about that. OK? All right. Let's move on to, like I said, one of my more favorite topics here. Cryptographic hashing. OK? See this number here? 05B528EF. It's hexadecimal. It's got letters up to F in it, right? 16, base 16. Right? Anyone know what that stands for? What that means in the code that it's related to? It actually is struggle bus. Right? Which really is the amount of effort you would have to put into figuring out that means struggle bus if you didn't know that it was struggle bus. Right? Cryptographic hashing is this idea that you can hash something such that it makes it very, very, very hard to figure out what the hash came from, which is the point, because you're trying to be sneaky about it. You're trying to pass this number on to various people who can, or for instance, who might want to do something with it, but you don't want the people in the middle that might get a hold of it to know what it is you're passing, right? So there's various ways of doing this hashing such that we get this sort of control over it, which is cool. Okay, it's very, very important to digital security. Anybody ever bought anything online? Yeah, if you bought something online, you have used cryptographic hashing behind the scenes. Okay, Amazon would not exist if it weren't for cryptographic hashing. Okay, Amazon.com, not the Amazon, right? Unless we happen to be a giant simulation like the Earth, but that's a different story altogether. Okay, so a cryptographic hash function is this. It's a hash function that takes any what we call arbitrary block of data. It can be any length, and it turns it into a fixed length string. Okay, such that any change to the original data would change the actual hash function, actually in a big way. Okay, the value. What did I say?
You said change the hash function.
Change the hash value itself. Yes. So in other words, we have this message struggle bus, right? And it hashes to this value here. And by the way, if you want to figure out what to do, if you want to make that number out of any message, you can actually do a little one-liner Python in your UNIX command line, and it'll give you that. Right? If you type this in, and it's small print, but you can look it up on the slide. If you type this in, it will print out this what we call the digest of that word, and that's what we want to get out of it. Okay? Yeah.
So is that just the regular standard
the standard Python library, yeah. There's this library called hashlib, which somebody wrote to do it.
Kind of defeat the purpose, since if it's a standard thing, anyone has access to.
Ah, careful. If you know the word struggle bus, you can create this. If you get this, you cannot go back and get struggle bus.
But don't we know how it took struggle bus and made it that
We do, but you can't go backwards. So there's this thing called a one-way function. This idea that you have a one-way function. So here, look. X mod 23 equals 4. What was x? I mean, you have any idea what x was? It could be 27. It could be 4. It could be, you see what I mean? It could be lots of different things. You might be able to limit it to some extent, but they write these functions very well, so you can't go backwards with them. Yeah?
But if we have the requirement, and it says that any change to the data will change the hash value.
Yeah.
Adding 23 to that wouldn't change it.
Adding 23 to that wouldn't. Right, you're right. This is not a good cryptographic hash function, but it's an example of a one-way function.
Anything that's one way, I feel like would have that. Like
it will change. Oh no, it will almost certainly change it. And that's why you have to design the right function. We're not going to go into details about those functions, but
so like that. The point is like that if that digest could only have come from that message.
Yes.
But then you can't tell the message from the digest. That's what I'm not like.
Right.
Can't,
Oh no, I know, but I know.
Things are hard to.
Oh right.
With each other.
Right. It is hard to reconcile with each other, but just look up a one-way function, and it'll show you that now it's not a one-to-one because there's an infinite number of messages you could write, and this digest is only 500 characters long or 128 characters long or something, right? So it's not an infinite. Like you will have some collisions, but part of it, and we're going to get to that in a minute, is it's really hard to find the collisions. So it's harder than you think to find those collisions. Charlie.
But I thought this was supposed to be an example for encryption.
Well, this is not. Right now. This is not encryption quite yet. This is basically saying come up with a hash of a value and turn it into this. Okay, not quite there yet. All right. So here's what a cryptographic function. Here's what we want out of our cryptographic hash functions. 4 ideas here. We want it to be easy to compute, which means just basically arithmetic if you can do it, right? Relatively easy to compute, although there's exceptions to that as well. We also want it to be infeasible to generate a message. In other words, come up with a message that gives you the hash that you do. Like in other words, unless you know struggle bus, you're never going to be able to come up with this number. Okay? That's another property of this. Similarly, kind of related, is it's infeasible to. Oh, sorry, that's the last one. It's the similarly. The third one here is it's infeasible to modify a message without changing the hash. You modify the message, the hash will change a lot. I'll show you an example in a sec. And then this one's related to 2, actually. It's infeasible to find 2 different messages with the same hash. If you've got message 1, struggle bus, and you have message 2, something else, it's very hard to find 2 messages that have the same hash, okay? Because we want them to be unique. Okay? Let's go through these one at a time. Easy to encrypt, it's easy to compute. If you have a lot of messages you want to hash, it should be relatively fast to do it, barring certain circumstances we'll talk about in a minute. It should be very fast to verify messages too. It should be very fast to say, does struggle bus go to this hash? That should be very fast to do. Okay, I mean they're kind of related. Okay, the next one, infeasible to generate a message that has a given hash. Okay, this is the passwords kind of idea. Okay, this is where passwords come into play. If my password was hello, okay, you don't want somebody else to have a password that matches the hash that my password goes to. Okay? You shouldn't be able to go backwards either. Okay? One thing that we use this for is if you hash something, you should be able to tell if that, like given the original, you should be able to tell that what was hashed came from that, basically. I'll show you an example in a second of that as well. Okay? You want these things to be unique, in other words. Okay? Here's the one that I promised you I'd show you the difference of if you change something in that message. So our message is struggle bus. It gives you 05B528 blah 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 blah. If we change it to struggle bub, 1 letter change, look at the difference in hashes. 4BFF5E versus 0B5. It's totally different. 1 change in a letter will make a totally different hash, and that's very good. Okay, it's very good for a couple reasons. Aaron?
Oh, well, what if you change it to something completely different and it just happens to be the duplicate? I know the chances of that are incredibly slim.
Then,
given the
yeah,
hugeness of the
right. That happens. Sure, it's possible. Rare. It's not gonna happen.
infeasible.
It's not infeasible. Sure. Yeah. Yanni?
I don't get how someone would like decrypt it then like
We're not really talking about decrypting this yet. We're talking about kind of encrypting such that you can decide whether or not. I'll give you a good example. Let's say I have a password. My password's hello, because I'm not a very good password creator, right? And hello happens to come to this, right? And your password, you're a little better than me. You use hello1, right? And hello1 doesn't go to something like this. It goes to something completely different. Here's why we like that. Because let's say that some sneaky person finds my password, right? They can get into my accounts. That same sneaky person gets a listing of all the hashes. If my password created a hash similar to yours, they'd be able to look at the two hashes and go, oh, Yanni's password is very similar. It might be hello1. And they try, you see what I mean? Like, so you have to be careful with that. Yeah.
the passwords. You said that you don't want the same password to like match the
Yeah.
hash.
You don't want them to.
Be one-to-one, but that would mean that we can go back.
You can't go back though. That's the beauty of it. I know it sounds like, how do you not go back if it's not one? It's not one-to-one, first of all. It's not one-to-one. But the space is huge. This number is a huge number. Look how many digits are in it.
It's very unlikely
Right?
that it's
Very unlikely that it's the same. Yeah, and that's the point. And you can find ones that are the same, but you keep increasing the number of digits here, and you're much less likely to do it. Yeah.
So I'm just like thinking like the types of times when you need something like this
Yeah.
could a lot of times like involve sensitive data. So
Sensitive data, kind of. This is more on the idea of passwords and deciding whether things are that you created them and so forth. We'll get to that. We'll get to that one in a little bit. Okay. You'll see. I've got a bunch more things we can talk about here. And of course, it's infeasible to find two. This is what we were talking about. It's not easy to find two messages that go to the same hash. Okay. You will get a collision if you try long enough, but it might be the heat death of the universe before you get one. Right? I mean, you could have one, but it's going to be a long time if you do it right. Okay. All right. Here's some examples. Okay. Everybody recognizes Alice from Alice in Wonderland, and Bob from Sideshow Bob from Simpsons, right? Normally, the cryptologists normally use Alice and Bob as good guys. Okay, so pretend these guys are good for right now. Alice is good, but pretend Bob is good. Normally they use Eve for a bad guy for whatever reason, like eavesdropping, whatever, right? But anyway, here's an example of using a hash table or a hash function, cryptographic hash function. It's a little hokey, but let's say that Alice says she's solved some hard problem, right? And she writes it down. And Bob says, oh, I want to try solving that problem, but I also want to make sure that you solved it before, or Alice wants to prove that she solved it before Bob did. But she doesn't want to tell Bob what the solution is. Okay, what she can do is she can hash her answer. Okay, and she can come up with this hash, and Bob has no idea what that means, and he can't go back and figure it out. It's almost impossible to do that, right? But he has that hash, and he has it when he starts working on the problem. And then he solves the problem. Okay, Bob solves the problem. Alice then says, here's my original solution. And Bob hashes the original solution and finds out that it is exactly equal to the hash that she originally gave him, meaning that the original solution was the one that she came up with. You get that? It's kind of an interesting idea. You hash something, give somebody the hash, and that proves to them that you had that information when you gave it to the hash, but they don't know what that information is. Right? So that's kind of neat. Yeah?
You give them the hash function too.
You can give them you give them the hash function as well. Yeah. But you don't give them the message. Right? You don't give them the message, but you give them everything else. Yeah. But Bob's trying to solve some problem that's irrelevant to the hashing part. He's just solving some other problem. Right? Okay? So that's an example there. Okay? All right. So passwords, as I said, are already one of the big things. You don't want to store your passwords in what we call clear text. If you ever go to a website and you forget your password, and then you type in "I forgot my password" and they email you your password, bad news, right? Number one, it's all of a sudden gone over the open internet, right? But number two, it means that they're storing your password in some way that they actually know your password. Okay? What should happen is that the password system should store the hash of your password. Remember, given the hash, you can't go back and figure out the password. So how do you figure out if a user is a user? When I log in, or when you log in, I type my password, I type cgreg, and then I type hello, because that's my password, right? Well, we don't want the system administrators to know my password. All they get is the hash of it. How do they know it's me the next time I log in? They make the same hash again, and they compare the hashes. So when you forget your password, and you call up the help desk, and you say, hey guys, can you send me my password? They go, we can't. We don't have it. We don't know what your password is. We never did know what your password is. Sorry. What we can do is reset it so that you have to go in and reset your password. That's the only way they can do it. They don't know any passwords, and they don't have any data that would get them to be able to give you your password. It's just impossible. They just compare the hashes. Okay, so that's kind of cool. Okay? You match the user's name with the hash, and you can't retrieve the password. Okay? So this brings me to the question I asked at the end of last class. Is there a case where we want hashing to be slow? What do you think? I wouldn't ask it if it was not, right? No, we don't. Yeah.
Well, sort of, when you want to protect some data,
Okay.
you don't want somebody to be able to go through and try a bunch of possibilities, hash all of them, and then check the hashes against each other.
OK, that's a good idea. Yeah, when you don't want somebody to be able to use the speed of hashing as a benefit, right? Yeah, that's exactly right. Yeah.
Like, say there's a limited number of possibilities, like a PIN number or something like that, where there's only 4.
Uh-huh.
And then so you only have, like, what, 10,000 things to go through. So
I see.
hashing would be really quick. And, like, go through, like, all of the
Yeah.
trees to get where it ends. If you make that operation very slow, then it takes much longer.
Yeah, it takes a lot of time. Now, normally with something like that, they just won't let you insert your password a number of times, or they'll have an actual delay in how many times you can put it in. But yeah, but that's a good reason. But there's another one, like not related to actually doing the actual password right there. Alex, what do you think?
I know that YikYak actually uses a deliberately slow hash because it computes the hash based on your device's MAC address and the system time.
Mm-hmm.
So in order to maintain it, uses like a variable speed hash, and then your phone sends over the system time when you hit send yak, and then
I see.
those times and the hashes.
Oh, interesting. OK, so it takes the amount of time that they can define the amount of time it takes. Like they can kind of figure that out. Interesting. So here's the reason that a lot of times we want this to happen. OK, Bob is now a bad guy. Let's say Bob steals a set of usernames. OK, and he steals the hashes associated with those usernames. He doesn't get the passwords because nobody keeps the passwords. They're clever enough to not keep the passwords. OK? Well, first of all, most hash functions, in fact, every hash function that we use to store your password is open to the public. And you can go look it up and figure out exactly how they hash your data. Why might that be a good idea? Logan?
It's verifiable and independently auditable.
Verifiable, yeah. You don't want some weird hash function that you have no idea if the NSA put some back door in it, right? Right? Now I'm going to get arrested because it's going to go on YouTube. But you don't want that to be the case, right? You want something that you can verify, I can verify that it indeed is a one-way function that has no backdoors and so forth. Now, you have to be smart to be able to do that part of it, but yeah, that's exactly right. OK, so Bob goes and he steals the hashes and the usernames. What he can do is he can say, I'm going to just start creating hashes, because I know the function to create the hashes. I'm going to start creating the hashes and keep a table of all the hashes based on passwords that I think people might use, right? I love my cat, right? Password, which is a huge password people use, password, right? And things like that. And once you do that, if it's fast to create this table, right, then he can create the table and then compare all the usernames and their hashes and say, oh yeah, Yenny's password was hello1, right? Because her hash is the one I came up with in this giant list. So if it takes a long time to create that list, that's a good thing. Okay, you don't want to be able to create the table quickly. Yeah.
How could we see like the hash that Tufts uses, or can we see that?
Yeah, if you look up Red Hat password hashing algorithm, it should come up on the internet somewhere. You can look at it. It's going to be written in C, most likely. So you want to take a long time to be able to do this. this table that is like it's called the rainbow table. I forget exactly why, but it's called the rainbow table. That's all the password hashes that you might want to use, right? And people do this all the time. Okay, you could probably look up the struggle bus thing on the. I used a pretty good one for that one, but there's some that are like you can look them up online, the hash, and it will tell you what it came from because people have done these tables for a lot of these types of hashes. Okay. So you want to what we call key stretching, which means stretch out the amount of time it takes to do your hash. Okay? Sometimes, though, you get hit by the fact that we have fast computers these days. And even if you have a slow hash function, the faster the computer, or if you're using GPUs, you can crack these passwords a lot faster by doing billions of hashes a second. Right? What they've done is they've changed it so that the speed of your CPU isn't the defining factor of how fast you can do these. You also have to have a lot of memory in some cases, and that can slow things down as well. So there's various other ways of slowing things down. But to answer the question, yes, you definitely do want to do that. Finally, has anyone ever heard of salting a password? Ever heard of that? A couple people have. If you take so Yenny uses hello1 as her password, and I use hello1 as my password, right? Both of us would have the same hash in the password table, right? So if somebody knew, or if someone got the hash table, they could look and say, oh, Yenny's password is here and my password is here, and it's the same hash, so we must use the same password. However, what they do is they say, no, no, no. Yenny's password is not hello1, it's Yenny hello1, and my password is Chris hello1. And they do the whole thing. That's called a salt, which is kind of like salting extra information in. And now our two hashes, even though we use the same defined password, have completely different hashes, and you can't go and figure them out. So it makes creating rainbow tables really hard. Yeah, Alex?
Wouldn't this also work if you just added a random long string, like the same long string at the beginning of any password? Because even if changing one letter of the...
Well, then if someone knows that random long string, they can then create a rainbow table of everybody's stuff. So that's the only other difference. It does help a little, but it doesn't help as much as using an independent word like your username, which isn't a secret, but when it's put in a hash, creates a completely different hash value. Okay? All right. So here's another example. File verification, right? And lots of open source software does this. In fact, you can go and check this out, right? If you want to know if the file you downloaded off the big, huge, scary internet is really the one that Mozilla wanted you to have for Firefox, you can go download Firefox. Okay? This is the latest version. Then you can go and find this thing called the MD5 checksum, which says, hey, we created a hash of the binary of the program, and we guarantee that if your program has the same hash, it's going to be the same program. Like exactly the same. And no backdoors, no steal your data, send it to, communist sort of thing, right? Okay? Right? It's going to be like this. So check with, what you do is you download the little check file, and then you run a little program called MD5 on it, which gives you the hash. You check your hash against the hash that they give you, and if it's the same, you know you've downloaded the right file. So it's pretty cool. It's a clever way of doing it. Yeah?
So if you know what Mozilla's hash is,
Mm-hmm.
and I wanted to create like a virus, but I wanted to make it look like it was Mozilla's
Right.
file, couldn't I just make my hash function come out to that no matter what?
You can't, because MD5 is really hard to find two messages that go to the same hash. Really hard.
Oh, so it's giving you the message, not the...
It gives you the checks. It gives you the hash value, right? And it's really hard to find two things that go to that same value. Really hard. Like you're not going to be able to do it unless you're super duper smart, like NSA. I didn't say that. Yeah.
I don't understand why you couldn't just give a different hash function out, or a different hash value out.
You could, but it wouldn't be for the. But you go to the Mozilla webpage and you say, what's the hash function for the program?
They're both coming from Mozilla.
Both coming from Mozilla. Yeah.
Okay.
Right. I mean, okay, sure, but yeah, all right. If but you know, hopefully you know that you go to Mozilla. If you downloaded Firefox from some other website, then you go to Mozilla and check, you'd know. Okay. All right. Let's see. I think we'll stop there because we're out of time. One question. Yeah, Nathan.
It's just a comment about what hashing.
Yeah.
Okay, so then just one thing that I find it's used for is verification, not just against tampering, but against, for example, when I download Linux versions,
Yeah.
I typically use torrent networks because you get fast downloads.
Right.
Because you download from the
platform, but it's possible that something got corrupted.
Ah, right.
Actually, that has hashing inside it, so it doesn't really need to. But you
Yep.
get the hashes, and if it downloaded wrong, then there's no use. Then you don't have to bother.
Oh, trying to install it. Yeah, that's a good point. So if you're using the Tor network to get your Linux build and it comes out, there's a mistake in it, that hash should be different. Absolutely. Okay. Any other comments? All right. No labs today and tomorrow. Have a good day off tomorrow. We'll see you on Wednesday.